Okay, 30 seconds. This because I'm out of time. Okay, any parting words before we go in? Okay. So as before, if you have any questions, put it in chat and I'll either see it and get to it during the QA session. As before, lectures are 60 minutes, 15 minutes of QA. I look at the chat list every lecture, and if you show up 5 times over the semester, you get full credit for class participation. It's one way to encourage you guys to join here. So let's get started. We've got, we don't have a lot to cover today, so we can just kind of take it easy. We're going to cover angular, I need to share that, sorry. If I screw up, I think last time I screwed up and forgot to share for a couple of times, just let me know. I get old. When you get old, you make mistakes. Here we go. You guys are young. You don't have an excuse. So today we're going to cover angular measurements, orbits, and Kepler's laws. These are kind of the basis for what we're doing. We'll be covering gravity and then special relativity in the next 2 lectures. Just to remind you, we have an exam not this week, but next week. So we have 2 lectures this week covering chapters 4 and 5. And then next week on Tuesday, we have 1 lecture finishing up 5, which will be on special and general relativity. I need to fix that. And then an exam on Thursday. Hold on one second. And so as I mentioned before, the exam is on Moodle. I'll open it up at like 9 a.m. You can take it any time during the day. I close at midnight. You have 7 minutes to take the exam. I believe right now there's 69 questions, and the questions are true, false, multiple choice, a ranking, and fill in the blank. I've gone over it like 3 times, making sure there's no mistakes. I've already posted the exam guide under resources in WebAssign that will tell you which topics they're on. The questions all come from the textbook, with the sole exception there'll be 2 questions from things I mentioned during the lectures that aren't in the textbook. That, again, just to encourage you guys to come to the lecture. Okay, last time someone asked about Synodic versus Sidereal, and I promised I'd talk about that, so here it is. Oops. So Sidereal versus, it's also called a solar dare. And you have to excuse me, I have trouble pronouncing words sometimes. I don't know, Synodic, I don't know how that's pronounced. I don't think I've ever heard anybody say that. How many minutes, how long do you take the exam? 75 minutes. Are there any problems that require a calculator? No. What if a teapot the size of Jupiter fell on the Earth? That's not going to be on the exam. How many minutes? Yeah, again, it's 75 minutes from the time you start it. So I think Moodle works where you can't come back and it keeps track of that time. It's like once you access the exam, you've got 75 minutes from that point. I think that's where Synodic, yes. I just say solar. So when we talk about a day or an hour or a year, we're always talking about solar. That's our definition of day. And by solar, what it means is You go from the sun directly overhead to the sun directly overhead. That's a solar day. A sidereal day is where you're measuring relative to the fixed stars, but that's not something that we normal humans do anytime. It's only something that astronomers do. So here is a graphic. If you can visualize this, you're looking due south in this particular graphic, and you are lined up with the sun and a star. And then 23 hours and 56 minutes later, you are lined up with the star right there, but not the sun. 4 minutes later, you're lined up with the sun. And so you can see here, you rotate around and you go to pointing to the same star, rotate just a little farther to point to the sun. So this is our definition of a year, of a day, is solar to solar. So a solar day is sun to sun, and a sidereal day is star to star. So question for you, let's say, forget leap years. If there's 365 solar days in the year, how many sidereal days are there in a year? Just put the what you think it is in the chat, please. Yeah, everything is on the resource folder in WebAssign. We do nothing in Moodle other than the exam. So all the files I want you guys to have, including these lectures, the lectures from the textbook, the exam guide, the syllabus, all of that stuff is on the resources in Moodle. So anybody have a guess of how many days, how many sidereal days there are in a year? So Art Shell says 364. That's a good guess. But Morgan Wright got it correctly. It's 366. And you can think of it this way. Every sidereal day is 4 minutes shorter than the solar day. You can actually fit 366 sidereal days in the same time it takes to fit 365 solar days. And again, that's because of that little thing there. So let's bring up a couple of simulations here. Okay. So you share. Okay. So here we go. One sidereal day. See, it's star to star. Let's realign to noon. One solar day is sun to sun. Okay. One sidereal day, star to star. One solar day, sun to sun. Okay. And so if we go, let's go through one solar day, and this clock actually goes reverse. We can do it here. Let's reset. You can see here, when I said about the 366, let me show you that. Let's reset here. And if we take it all the way around, we've gone 181 solar days and 181.5 sidereal days. And if we go all the way around, then we get to 366. Okay. So again, solar is sun to sun, sidereal is star to star. Questions? So let's go back. Okay, enough about that. Today we're going to be covering orbits and Kepler's laws. And this is going to get back to the dead white guys. Last time we talked about Copernicus, who came up with what we call the heliocentric, sun-centric version of the universe. That was in the 1540s. And then 60 years later, we've got Galileo, Brahe, and Kepler, who were all contemporaries. Galileo, we talked about a little bit. Galileo discovered that the universe was a heliocentric universe, not a geocentric universe. What he discovered was that the Venus had phases. We went over that in some detail. There's mountains on the moon, and Jupiter had satellites that went around Jupiter. And so he was what we would call an observational astronomer. He observed things using this newfangled telescope. Then we had two theoretical astronomers. We had Brahe and Kepler. And we'll cover those in detail. And then we'll wait until the next lecture to talk about Newton and gravity. Newton and Einstein are the two greatest human beings that have ever existed on the planet, in my humble opinion. Okay, so we've got two sets of laws that you need to know for the exam and for this course. We've talked about Newton's laws at the top there. Today we're going to be talking about Kepler's laws, and there's three of them. Orbits are elliptical. Orbits sweep out equal areas and equal times, and the square of the period equals the cube of the semi-major axis. This looks complicated. It's not. We'll be talking about that. And again, you shouldn't be afraid of that because you all have had algebra. This is the formula sheet from the formula file that, again, is posted on WebAssign under resources. And the equations we'll be talking about today. Here is the p squared equals a cubed that we talked about, and I think there was a homework question or two on it. And here is the small angle formula, which again we talked about, and we're going to talk about both of these in some detail. So angular measurements, orbits, Kepler's laws, that's today's lecture. So angular measurements, again, this is just a refresher. Angles are everything in astronomy because we often don't know the true sizes. All we know is how far apart things are in the celestial sphere. We measure distances on the celestial sphere with degrees. You're all familiar with degrees. Each degree is broken up into 60 arc minutes. Each arc minute is broken up into 60 arc seconds. The sun and the moon are half a degree or 30 arc minutes in size. Human vision has an acuity of about 1 arc minute, and ground-based telescopes typically have a resolution of 1 arc second. Okay, so ground-based telescopes typically can see things with 60 times better resolution than your naked eye. So so here's some examples here. This is 10 arc seconds. And again, you couldn't see any of these visually. This would all be using telescopes. And you can see here, well, we'll go back in a second. And to measure what the true size of this is, we use the small angle formula. Actually, let's go back here. So this Jupiter is about 30 arc seconds across, 34 arc seconds across. Here is Mars, that it looks like it's about 20 arc seconds across. And again, the resolution, this is actually pretty good resolution. The resolution that you can see is, again, with a telescope, is about 1 arc second. Mars looks almost the same size as Jupiter, even though Mars is 1/10 the size of Jupiter. And that's, of course, because in this picture, Mars is a lot closer to us than Jupiter. Jupiter is much, much farther away. And then Saturn is about the same size as Jupiter, but it looks smaller, again, because Saturn is much farther away. Venus always looks fuzzy because Venus has an atmosphere caused by runaway global warming. I actually read an article yesterday where someone thinks that global warming was created by some advanced species that killed themselves by polluting their atmosphere. Anyway, small angle formula. What do we need the small angle formula for? Well, sometimes if we can actually calculate the distance to an object, then we can figure out, based on its angular size, how big it is. Or vice versa, if we know how big something is, we can figure out how far away it is. Okay, so that's why the small angle formula is useful. Here is the mnemonic that you should have all memorized from geometry in high school. Sine over hypotenuse. The sine is equal to the opposite over the hypotenuse. So that the opposite would be the y over the hypotenuse, which is there. The cosine of an angle is equal to the adjacent, in this case x, over the hypotenuse. The tangent is equal to the opposite over the adjacent, in this case y over x. So this is something you should just memorize because you're going to be using that throughout your whole lives. How did old white guys calculate the distance to celestial bodies? They didn't. So a lot of this course is going to be how we figured out distances. And the dead white guys had no way of calculating those distances. So they just had to wonder how big the universe was. And if we told those guys what the actual size of the universe, it would have been incomprehensible. They couldn't understand it. Can you explain how to get the semi-major axis? Patience. Okay, so here, tangent of angle is opposite over adjacent. There's opposite, there's adjacent, y over x. Here's the thing. If you map the tangent of the angle as a function of angle, here is the sine curve, there is the tangent curve, and that is actually the curve of the angle as mapped as a function of the angle. Notice that here, the tangent of the angle, and the sine of the angle, again, all these expressed in radians, not degrees, they're all approximately the same. So for those of you that have never used radians, well, actually, you've all seen radians at some point. Radians are just another way to measure degrees. Astronomers typically don't use radians except in this particular case. The reason we use radians, and again, radians, the difference between radians and degrees is you multiply degrees by pi over 180, or you multiply radians by 180 over pi to convert it. 180 over pi is the conversion factor. So there's 2 pi radians in a circle, there's 360 degrees in a circle. The reason we use this is because in radians, the tangent of the angle is approximately equal to the sine of the angle is approximately equal to the angle. Again, in radians, not degrees. So here, the small angle formula is, if you know x, if you know the distance, I can tell you the size, given the fact that you probably know the angular distance, how many angles it subtends on the celestial sphere. And the tangent of the angle is approximately equal to, the sine of that angle is approximately equal to the angle itself. So this small angle formula is incredibly useful. Again, in radians. So here is the equation that is quoted in the textbook, but one thing to be careful of, to get this angle in radians, you just get y over x. Okay, so if you know either y, which is the size, the linear diameter, or the distance, you can get the angle in radians. This equation is a special version of this equation. This equation is only if you don't want to bother doing the conversion from radians to degrees and then from degrees to arc minutes and arc seconds. Typically, we're dealing with things pretty small. We're dealing with things that are in the arc second thing. And so there we can use this equation to directly convert this y over x into angular diameter in the units of arc seconds. Okay. I had a question, somebody had homework and they just plugged and chugged, not realizing that the question was asking for degrees, not arc seconds. So if you want the answer in arc seconds, use this equation. If you want your answer in radians or degrees, use this equation. Why wouldn't the small angular formula work for calculating distance? It does work for calculating distance if you know the size of the object. Okay. Will the exam clarify what unit is expected for each problem? Absolutely. As did all the homework problems for that matter. Okay. So here's the thing. So here's, this is the graphic that I was trying to show you. That's 364. So here's the thing. You can have things that have the same angular size, but have different sizes, different physical sizes. So here we have a small thing that's close and a large thing that's far away, but they subtend the same angular size on the celestial sphere. Okay, so just because something is large or small in the celestial sphere, it doesn't really tell us whether it's really large or small because we don't know the distance. Only when we can calculate the distance can we actually calculate its true size. And that's why astronomy spent and continues to spend an enormous amount of time to figure out distances. In fact, we have something called a distance ladder, where we got 6 or 7 different techniques for calculating distance, and they all overlap, and they create this ladder where we can figure out the distances to the most distant objects in the universe, which are 40 billion light years away. But we'll be getting into that in a bit. Now let's talk about orbits a little bit. There's an art to flying, or rather a knack. The knack lies in learning how to throw yourself at the ground and miss. Okay. So here's Isaac Newton, a schematic. He throws a ball. The ball goes a certain distance. He throws a ball again. It goes a distance. Notice that the harder he throws the ball, in other words, the more horizontal velocity he gives the ball, the farther the ball travels before it hits. And that's because we've got this constant acceleration that's trying to pull the ball down. And so it might take, say, 2 seconds for the ball to fall. And if he throws it at a much higher velocity, he can go much farther in those 2 seconds. Okay. But here's the thing. The Earth is not flat. Now, it looks flat, but we know through trillions of measurements and the fact that we've had people in orbit, the Earth is not flat. So here we throw the ball. It goes a certain distance. We throw the ball again. It goes farther. But notice here, instead of 2 seconds to drop from here to here, we have a lot more than 2 seconds. And that's because I've thrown the ball, and by the time the ball actually hits the Earth is actually curved down. Again, this is because the Earth is round. So the question is there a speed that I can throw this ball so it never actually hits the surface? It just continues to go around. And the answer is yes. And that speed is 17,500 miles an hour. Okay, and that's called the orbital velocity of the Earth. And that orbital velocity of the Earth, not this lecture, but in a future lecture, we'll give you an equation for that you'll be responsible for. But that orbital velocity depends on the mass of the object, depends on the radius of the object. And so for things that are not very massive, it's very slow. So for instance, an asteroid, the orbital velocity is basically walking speed. But here it's pretty fast, 17,500 miles an hour. Not a lot of things go that fast. And that's one reason it took thousands of years for us to figure this out. The person who figured that out was Isaac Newton, who couldn't possibly have had access to technology to actually put this in, bring this into fruition. So it was just an amazing coup for him to theoretically understand the concept of orbits. Being in orbit is just constantly falling and missing. So here's the thing. When people are in the International Space Station, they aren't weightless. They're just falling. They're falling just like you are skydiving. And statistically, a couple of you have skydived. And so those first couple of seconds before air resistance grabs you by your hiney, you are experiencing exactly what it's like to be on the ISS. The ISS is basically those 2 seconds of free fall when you first jump out of the plane, except instead of 2 seconds, it could be a year. So the simplest orbit is a circle where you just continually fall. It's not the only kind of orbit. And we'll talk in the next lecture about why there's different types of orbits. So there's orbits that are ellipses, if you throw harder than 17,000 miles an hour. And there's orbits that are called a hyperbola. And a hyperbola, you're throwing it so hard that it actually never comes back. Okay. And those are, you will hear the term conic sections. And this is a mathematical thing. If you take a couple of inverted pyramids and you slice them with the plane, if you slice it horizontally, you get a circle. You slice it at an angle, you get an ellipse. You slice it at a certain angle, it's a parabola. And then if you slice it at a very thick angle, it's a hyperbola. And notice that parabolas and hyperbolas, they never return. They just go off into infinity. Something that's interesting is a couple of years ago, there was an asteroid called whatever that word is. And it was sailing through our solar system, and that in itself is not unusual. This is, by the way, not a picture. This is an artist representation. What was unusual was, and we see hundreds of thousands of asteroids spewing through our solar system every day. So 1 out of 100,000 isn't unusual. Which was unusual about Umama, whatever you pronounce it, is the fact that all the other asteroids we have observed, every single one of them was either on a circular or an elliptical orbit. This was the first one we had ever observed that was on a hyperbolic orbit, which meant that it was coming in and it was leaving and it was never returning, which meant this was not part of our solar system. This was an interstellar visitor. So anyway, you, Obama asteroid. Whoa, mama. Yes, right. Just thought I'd pass that on. It was on a hyperbolic orbit. That will be one thing that may or may not be on the exam. Okay. So that was about orbits. We're going to be coming back to orbits over and over again. Today's lecture, Thursday's lecture, and Tuesday's lecture, because orbits are important in astronomy, as you might guess. What we're going to do is we're just going to go through Kepler's laws, ask some questions, and that's basically the lecture. So we've got some time for lots of questions this lecture. Again, coming back to Galileo, we've talked about that. Galileo observed the universe with his telescope. The church wasn't real happy about that. We've got Brahe and Kepler. So today we'll talk about Brahe and Kepler. Thursday we're going to talk about Newton. Johannes Kepler. There's a picture of him. Really, the only pictures I've ever seen of him are variations of this. He was a quiet teacher who liked to keep by himself. He spent 20 years working on this theory. He was brilliant, but nowhere near as brilliant as Newton, and we'll get into that. But what he did was, for the time, made an amazing intellectual leap. A leap that nobody else really could have done for reasons that I'll get into in a minute. He worked with Tycho Brahe. I'll talk about Tycho Brahe in a little bit. Tycho Brahe was a very colorful character. And so Johannes Kepler was a mathematician. He didn't dirty himself without. Tycho Brahe was one of the richest people in Europe at that time. And Tycho Brahe built the greatest observatory that existed at the time. And remember, this is before telescopes. So their definition of observatories were instruments that could measure positions very, very precisely. And by doing that, you could map the motion of planets, the motion of stars very, very precisely, even if you didn't have a telescope. And he found that planetary orbits were neither circular or uniform. Why is this important? This is important because up until this time, everybody assumed that, even Copernicus assumed that there was some perfection to the universe, that even if the universe was solar based, at least things moved in perfect circular orbits around the sun. And in fact, Brahe spent like a decade of his life trying to fit perfect spheres and perfect squares and tetrahedrons, perfect solid objects into these, what he thought were perfect circular orbits around the sun. Even Copernicus thought that the orbits were perfectly circular, which is one reason why the Copernican theory didn't really work well in terms of predictions. So Brahe, Kepler was the first person to make that intellectual leap, that the universe really is kind of messy. It's not perfect, okay? The perfection, to my mind, the perfection is in the theory of gravity, which is a single equation. But the perfection is not in the instantiation of gravity. Just like we have maybe perfect laws of genetics, but when you get into details, those perfect laws of genetics become very messy, and the types of organisms that come from that perfect laws of genetics are themselves very messy. Okay, so and he wrote down the 3 laws of planetary motion, which we're going to go over in great detail today. So let me just do a side thing on Tycho Brahe, that really rich guy. Here's a picture of him. The thing that's notable about this picture is it shows him with an intact nose. Because later in life, he got into an argument with someone. And when you get into an argument at this time in Europe, you pull out your sword, and his opponent sliced off his nose. And so he spent the rest of his life with a nose made of gold, again, because he was rich. Another picture, and again, they didn't show that gold nose. Here's a picture, a drawing of his observatory, and no telescopes, but you certainly had instruments that could measure angular positions very, very precisely. And here is one of a schematic of one of those instruments where you would see a light that would fall on this very large arc here, again, to measure positions as accurately as possible. So that's another interesting fact that is not on the slides, that Tycho Brahe had a prosthetic nose, a prosthetic gold nose. Okay, Kepler's first law. The orbits of the planets are ellipses with the sun at one focus. So an ellipse is defined by what's called the major axis, which is the distance between the fat part of it, and then the minor axis, which is the distance between the skinny part of it. Here's a...
In 1609, Johannes Kepler published Astronomia Nova, a book containing 10 years of his efforts to understand the orbit of the planet Mars. He was using state-of-the-art astronomical observations from his mentor and employer, Tycho Brahe, who was famous for generating an enormous amount of high-quality data, and he needed to find the best explanation for the motions of Mars, a very tricky problem. There were 3 models of the solar system out there at the time, but none of them worked very well for Mars. First, the Ptolemaic system put the Earth at the center, with the sun and planets orbiting it in perfect circles. There was also Copernicus's heliocentric model, which set the Earth among the planets revolving around the sun. And finally, Tycho had his own system to propose, which combined aspects of both. He put the Earth at the center with the sun and moon orbiting it, but let the other planets orbit the sun. All 3 systems relied upon circular orbits, because a circle was accepted as an ideal shape. Copernicus, Tycho, and Galileo all believed that planets should travel along circular paths, but the data just didn't fit. Instead, Kepler found that another shape, the ellipse, works a lot better. An ellipse is sort of like a flattened circle, and it has some special properties. You can draw one by taking a loose string, attaching both ends to the paper, and using a pencil to keep the string taut while moving all the way around the perimeter. The result is an ellipse. The length of the string never changed, meaning that the sum of the distances between each endpoint or focus and any point on the ellipse is constant. In Astronomia Nova, Kepler states that Mars travels in an elliptical orbit around the sun, which is at one of the foci of the orbit. Later on, he expanded this first law to include all of the planets and demonstrated that this shape fit the available observations. The further apart the 2 foci are, the longer and skinnier the ellipse. And this skinniness parameter is called eccentricity. Comets can have very eccentric orbits, coming in quite close to the sun before traveling back to the outer reaches of the solar system. On the other hand, in a perfect circle, the 2 foci would lie right on top of each other, right at the center. The orbits of the planets in our solar system are not very eccentric at all. They're really very close to circular, which is partly why perfectly round orbits seemed like a natural thing to expect in the first place. It wasn't easy to abandon a central idea like that, but with his first law of planetary motion, Kepler rejected circular orbits and showed that an ellipse could better explain the observed motions of Mars. Generalized to all planets, it states that the orbit of a planet follows an ellipse with the sun at one focus.
Okay, let me show a brief demonstration. Okay, so here's an ellipse demonstrator, and this E is eccentricity. This is the eccentricity tells you how elliptical the orbit is. So the eccentricity of a circle is 0. as we make the circle fatter, you got these two foci, and notice the eccentricity gets bigger and bigger. And if the eccentricity was 1, you just have a line, okay? So eccentricity of 0, eccentricity of 1. And as I make this bigger, notice that the semi-major axis, so the major axis would be this. This is the semi-major axis, A. Make it bigger or smaller, is there, okay? So anyway, let's go back. So that was Kepler's first law, which of course you'll be responsible for. Kepler's second law is that the planets, as he said, sweep out equal areas at equal times. Another way to think of it is the closer the planet gets to the sun, the faster it moves. Now, when we get to Newton and gravity, it will be very clear why that is. But right now, this was a law that he had developed, a mathematical law that he had developed empirically. And this is actually completely true. It's still true today. In fact, all of Kepler's laws are true today, and we use Kepler's laws to actually calculate the orbits of the planets and the motion of satellite probes going through the solar system. Okay. So, question for you: when the Earth is moving, when is the Earth moving fastest in its orbit? Let me bring up that poll. Lecture05. We haven't really talked about this, but I think this is an interesting question. And again, the questions are not graded, but they will help in the discussion. Okay, 5, 4, 3, 2, 1. Wow. Okay, we have a tie. We have a tie between January and July. That's very interesting. The answer is, as we talked about last time, the seasons are due to the tilt of the Earth's orbit. And it just so happens that the Earth is closest to the sun in January, okay? And even though that doesn't seem to make sense because it's cold here in January, but remember, it's hot in the southern hemisphere. And so the Earth's orbit is almost nearly circular. It's not terribly elliptical, unlike Mars's orbit. But it is a little bit closer in January. And so the people that selected January, correct. We actually, I don't think I mentioned that in lecture, but it's just interesting to note here that again, the Earth is closest in January. So Kepler's second.
Thanks to the meticulous astronomical observations of his colleague and employer Tycho Brahe, Johannes Kepler was able to test several rival hypotheses for how the sun and the planets are arranged in the solar system, eventually leading to his 3 laws of planetary motion. In 1609, he published the first 2 laws in a book called Astronomia Nova, which focused on the movements of the planet Mars. Mars was something of a conundrum. Its observed motions didn't match any of the proposed models of the solar system, which involved circular orbits. Kepler's first law states simply that Mars travels in an elliptical orbit, with the sun at one focus of the ellipse. Although he chose to list it first, Kepler only came to this conclusion after figuring out his second law, which says that if you draw a line from the sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as Kepler's equal area and equal time law, and this law works because Mars doesn't move at a constant velocity. It speeds up the closer it gets to the sun. So if Mars is approaching perihelion, the point in the orbit nearest to the Sun, it's traveling faster than if it's at aphelion, the point that's farthest away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slowly. Either way, the area swept out in a fixed amount of time is the same. Kepler and his contemporaries could see that Mars doesn't move at a constant rate, but they didn't know why. This inverse relationship that Kepler proposed between distance from the Sun and orbital velocity could explain the puzzling observations of Mars' movements, but only if the orbit is an ellipse. A circular orbit would mean no change in distance from the Sun with time, and thus the velocity would be constant as well. These two statements, that Mars travels in an elliptical orbit and that its speed varies so that the Mars-Sun line sweeps out equal areas in equal time, were generalized to include all planets in 1621, and they constitute Kepler's first and second laws of planetary motion. The second law, it turns out, is also a consequence of the conservation of angular momentum, which was not a concept known to Kepler in the 17th century. Angular momentum is a measure of the amount of rotational motion in a body or system of bodies, like Mars and the Sun, and in the absence of outside forces, it's a fixed quantity. This implies a trade-off between the distance at which Mars orbits and its velocity, like Kepler noticed. Just as an ice skater spins faster after pulling her arms closer to her body, Mars has to move faster when it gets closer to the Sun. Kepler's statement that the area swept out by the Mars-Sun line is constant is equivalent to the statement that angular momentum is a constant as well. That is to say, that it's conserved.
Okay, that's Kepler's second law. We got one more law to go to. So will we need to know years for the exam? So doesn't the first law really imply the second law? No, the first law does not imply the second law. The first law is the shape of the orbit. The second law is the speed that you are going on the orbit. So they're separate laws. Now, both of them are derived directly from gravity, which wasn't enumerated until 60 years later. It's going to take you to go around the object. Semi-major axis. And here's
Kepler's first and second laws of planetary motion appeared in their earliest form in 1609 in the book Astronomia Nova. They state that 1. Planets move in elliptical orbits about the Sun, which sits at one focus. And 2. A planet's orbital velocity varies over the course of one revolution, such that a line drawn between the planet and the Sun will sweep out equal area in equal time, wherever in the orbit you are. Kepler published his third law 10 years later in his 1619 book Harmonices Mundi, or The Harmony of the World. By sifting through observations of how the planets move in their orbits, he noticed something curious. The time it takes for a planet to orbit the Sun once, its orbital period, p, is related to its average distance from the Sun, its semi-major axis, a, in a very specific way. The square of the period is proportional to the semi-major axis cubed. In fact, if we choose our units carefully with the period in years, the time it takes for Earth to go once around the Sun, and the semi-major axis in astronomical units, or AU, the distance between the Earth and the Sun, about 150 million kilometers, the proportionality becomes an exact equation. The square of the period is equal to the semi-major axis cubed. Let's try it out. Earth's semi-major axis is 1 AU, because that's the definition of an astronomical unit. Mars is farther from the Sun. It has a semi-major axis of 1.524 AU. We can use Kepler's third law to figure out how long it takes Mars to complete one orbit around the Sun. That is, how many Earth years make up one Mars year. The semi-major axis 1.524 AU cubed equals 3.54, and the square root of that gives us Mars' orbital period, 1.88 Earth years. Sure enough, Mars takes 687 Earth days to orbit the Sun, which is 1.88 Earth years. And this works for all of the planets in our solar system.
Okay, so let me show you a quick simulation of all of Kepler's laws, actually. Okay, so here's an orbit simulator. We can. This is the orbit for Mercury, and notice in this case, Mercury has an eccentricity of 0.2. And it's elliptical. There is the the sun is at one focus. There's the other focus. This is fairly elliptical for our solar system. Here's the center of the orbit. Okay. And so let's do this for Pluto. Okay. And Pluto also has a very high eccentricity of 0.24 here. And it's barely moving, so let's increase the rate. Okay. And you can see here are the orbits of the other planets, and look at Pluto's orbit. It's just kind of bonkers. So let's go to Earth and look at the eccentricity here. It's going awfully fast. The eccentricity is 0.017. So it's almost perfectly circular. Okay. And note here that the empty focus, and the sun is one center and then the empty focus is the other, they're almost on top of each other. Again, showing that this is a very, very circular orbit. Let's look at Mars. And here Mars has an eccentricity of 0.093. So it is a lot more elliptical than the Earth, but nowhere near what Mercury or Pluto has. So this is the first law. Second law. Let's speed this up a little bit. Actually, let's go to Mercury so we can see things. Okay. So you can just see visually. Let's clear all that. Where it sweeps. Let's try it again. And you can just see visually how these all have the same area. Oh, look, you can move them around. Cute. Okay. I've even seen people cut up a pizza pie like this. Okay, that's the third law. And Kepler's periods. Let's clear everything. Reset. And here is the period where we have the period in years and the semi-major axis, and they have this relationship here of p squared equals a cubed. Okay. And if you measure the period in years and the a in AU, then this is exact. So p squared equals a cubed. This is for the Earth and solar system orbits. And there's Mercury and there's Venus. Okay, and notice that they follow that curve exactly. And so here's Venus, 0.615, which is the period in years. And the distance from the sun is 0.723. Square that and cube that, and you get 0.378. So they follow that curve exactly. Okay. Does the eccentricity contribute to the changing of the seasons? Not sure if you answered this already. So Luke, so for planets like Mars, which have a fairly elliptical orbit, in fact, let me show you that. So Mars, as you can see, is fairly elliptical. And there is definitely effect on Mars because the Mars does get quite a bit closer to the sun in one part of its orbit. But remember, the Earth's orbit is almost circular. And so the eccentricity of the Earth's orbit contributes basically nothing to the seasons. What does the eccentricity contribute to? Anything? If you're talking about the Earth's eccentricity, Well, it does complicate calculations a little bit, and because you remember, here's something that's interesting that it does contribute to. So let's go to Earth. Well, no, let's go to someplace that is certainly more eccentric, and let's get rid of the solar system. Let's get rid of those. Oh, this takes too long. Let's go to Mercury. Okay, so here in an orbit that's fairly elliptical, what you can see is that these are equal areas and equal times. But remember, a solar day is from sun to sun. When you're out here in this orbit, the sun to sun, there's not a huge difference between that angle and that angle. But here, as you get close to the sun, there is a large distance between sun to sun. And so what that means is the length of a solar day varies depending on where you are in the orbit. So here, a solar day would be, relatively short compared to the solar day here, because not only do you have to spin to get to this angle, you have to continue to spin a little farther to get to this angle. So the solar day here is quite a bit longer than the solar day here, because you have to make that extra rotate to get to this new angle. What that means is our solar day on the Earth varies over the year, and it varies considerably by up to, I think, a minute or so. Now, we don't adjust our clocks to match a solar day perfectly, but what this means practically is the sun is not perfectly directly overhead at exactly the same time at noon over the entire year. It will vary by a minute or two on either side of that. So that's the one thing that we notice. So could it correlate to seasons in that regards? Yeah. So theoretically, you could measure the seasons by the length of the day. But like I said, it's so small, I'm not sure the ancients ever did that. Anyway, we got some questions before we go on. And then we'll open it up for the QA session. Okay, so there it is. P squared is proportional to 8 cubed. After you measure the year, period in a year, and the distance in AU, then that's exact. Okay. So let's get some questions. What hero of the Renaissance postulated the 3 laws of motion? You had better get this one correct. Okay, 5, 4, 3, 2, 1. So of course, the answer is Kepler, because we just covered that. Copernicus never postulated the 3 laws of planetary motion. Copernicus was identified with creating the heliocentric universe, the sun-centric universe, but he used circles, so he didn't. It wasn't good as a mathematical prediction. Okay. Okay. So certainly Newton had 3 laws, but they weren't the laws of planetary motion. They were the general laws of motion. Okay. Kepler's first law of motion states that, let's see. Kepler's first law of planetary motion states that planets orbit the sun, orbits are non-circular, orbits are elliptical in shape, And all the above are correct. Why did these guys propose 3 laws? Kepler had 3 laws and Newton had 3 laws. They can't to 4, that's correct. Good question. I don't know. I think 3 laws are easy to understand. You know, the Isaac Asimov's 3 laws of robotics. You know, Moses brought down the tablets with the 3 laws of living. The 3 commandments. Wasn't that right? The 3 commandments? Okay. And in this case, all the above are correct. The orbits are for the most part, non-circular. I suppose there could be a perfectly circular orbit. That would be statistically unusual. Orbits are elliptical in shape, most definitely. The planets orbit the sun is certainly part of that. But certainly the most important one is orbits are elliptical in shape. But this question, the way it's worded, is all of them are correct. Okay. You should get this one correct. Earth is closer to the sun in January. From this fact, Kepler's second law says, yeah, Arthur Clarke had 3 laws. What were those laws? So in regards to the sun days, was the counter Rigote based off both the orbit in relation to the sun and in relation to the stars? Yeah, good question. I don't think that the ancients had the technology to separate those two. Because the difference between the actual solar day as it varies around the orbit is very minuscule. What scientific revolutionary made the most important discovery that was not accepted until long after its death? Copernicus is the one that comes to mind, because he didn't publish his results till after. So certainly the Earth orbits faster in January, no question. And let's do this last question, and then we'll just open it up for questions. Kepler's third law relates a planet distance from the sun and its orbital. So Laurel, Pluto has the most elliptical orbit, and Mars is a close. I'm sorry, Mercury is a close second. Five, four, three, two, one. And the third law most definitely is about the period, although you could make the argument for the others, but it's really about the period. P squared equals A cubed. Okay. So that's it for the presentation today. I'll open it up for questions. Feel free to turn on your mic if you like. Let's see what we got in chat. How different would our lives be if the eccentricity was slightly increased for Earth? I don't think our lives would be that much different. It might make the seasons a little bit more or less intense. If the elliptical, I don't think life would be on this planet, because it would make the ecosphere too chaotic. Will the questions on the study guide be on the test? The study guide lists not questions, but topics. And so as you go through the textbook, definitely study the topics that are on the study guide. Let's see, where are we? How different what are some of the major developments right now? We'll be covering that in this course. Major developments are dark matter and dark energy, which we'll be covering, and is covered by, somebody asked about who's the most interesting astronomer today. I kind of flippantly said Katie Mack, who's my colleague and also teaches this course. But she just came out with a book that has become very widely successful, called The End of Everything. She's a cosmologist, and that's her specialty is dark matter, dark energy, and what that means. And we'll be covering that in this course. What planet is, let's see. How should we clear space debris? Good question. I don't know the answer to that. That's a very, very hard problem. And we have people like the Chinese who are blowing up satellites in low Earth orbit and just polluting low Earth orbit. It's just beyond belief. How hard is it to throw a planet's orbit? Well, pretty hard. Planets weigh a lot. However, one of the things we discovered when we were exoplanets was our solar system is very unusual. The fact that we have these large planets, Jupiter and Saturn, that are on the outer reaches, and we have planets on the inner reaches, we thought was common, but in fact it's extremely unusual because planets over millions of years usually migrate in and out. Can you go over the Obama asteroid and how it is not part of the solar system? It's not part of the solar system because it was moving too quickly. It was moving so quickly that it couldn't orbit the sun. So it was coming in, it was screaming in at a very high rate of speed, and we knew that the sun's gravity wasn't strong enough to keep it around. And so because of that, we knew that it wasn't on the sun, which meant it had to come from someplace other than the sun. So what gave Kepler the idea that orbits are elliptical? The problem is that when Tycho Brahe had the most precise data on the position of anybody else before and since, except when they got to telescopes. And that data showed that there was no way you could make circular orbits work. It didn't matter what speed you used for circular orbits. The orbits had to do something other than uniform speed. And it took him 20 years, but it was his genius to try and map these with elliptical orbits where the orbits sped up and slowed down depending on how close they were. And this is before the concept of angular momentum. This is before the concept of gravity. And this is certainly before computers, when you could just let the computer run with the data and the computer will spit out an equation that matches it most closely. So it was his genius to be able to figure out that if you put in these elliptical orbits, all of a sudden he could match the data exactly. What's the difference between a meteor and an asteroid, and which one killed the dinosaurs? So an asteroid, we have literally millions of asteroids in belts. The two major belts are the ones between Mars and Jupiter, and the one beyond the orbit of Neptune. A meteor is in many cases can be considered a synonym for an asteroid. Asteroid usually refers to things that have nothing to do with the Earth. A meteor is referring to something that comes close to the Earth. It's called a meteorite when it actually comes through the Earth's atmosphere. So really, we're talking about a matter of semantics. We're talking about an object probably about 10 kilometers across that impacted the Earth and killed off the dinosaurs. We project that something of that size will impact the Earth a few 100 million years. So the timing works out about right. We have mapped virtually all asteroids of that size, and none of them are going to hit the Earth anytime soon. So we're not going to wipe out the dinosaurs anytime soon. How do you find the orbital period AU distances, like for an elliptical orbit? So the p squared equals a cubed is for the semi-major axis. So it'd be the long part of the axis, that the radius of the long part of the axis. Where is the study guide? The study guide is a file called Exam1 that is posted in resources on WebAssign. While I'm talking about WebAssign, I should mention you guys should really go to the student forum, because although in fact, none of you have posted anything in the student forum, every time a student asks me a question about a homework problem, I post my answer there in addition. And so check there first before you email me, just for if you have a problem with a particular question. Because if you have a problem with the question, chances are lots of other people have had the problem. Kepler more the mathematician or astronomer? Definitely mathematician. Absolutely. He was looking at data. He never really looked at the celestial sphere at all. That was something that Brahe's minions did. If you like 2001, you should watch Beyond the Black Rainbow. I will look at that. Is that a video? I told you I have a special relationship with 2001. I co-sponsored a celebration for HAL 9000 in the year 1997, the year HAL was born. And then I was on the panel when they presented HAL 2001 at a film festival I co-sponsored 70 millimeter. Well, we have the basic equations of the exam calculated. There are no calculations on the exam. But you should definitely memorize the equations that are on the formula sheet. Who is the guy that cut off Brahe's nose? I actually do not know the answer to that. Who's your favorite astronomer of all time, as opposed to physicist or mathematician? Oh, in terms of a pure astronomer, that would have to be Hubble, who was, not only told us that the universe is much bigger than we thought, that these things that look like nebula were actually island galaxies, but also said that the universe is expanding against each other. One of the most brilliant astronomers. Now, there's people who are more brilliant than him, but I wouldn't call him an astronomer. Certainly Albert Einstein, nobody would call him an astronomer. Will we use the K within Kepler's third law equation? No, would most definitely not. We're just, in this course, it's p squared equals a cubed, where P is in years and A is in AU. I'm assuming it would be a good idea to have a calculator for the exam. You won't need it. You're welcome to have one, or you just use your computer calculator. Doesn't the sun revolve around its barycenter? Yes, it does. So the barycenter, I don't have an exam about barycenter. Barycenter is the point at which both objects revolve around. So the best way to consider it is like the center of mass. So the barycenter of the orbit of the Earth and the Sun is, I think it's like a few centimeters from the center of the Sun. The barycenter of two objects that are exactly the same mass would be equidistant between those two objects. But again, I don't think that we have that on the exam. Did you say that Obama asteroid was on a hyperbolic orbit? Most definitely yes, because a hyperbolic orbit is an orbit that's never. Does space make sounds? Well, it's interesting. Certainly people have yelled at science fiction movies, hear explosions. And certainly from that point of view, no. But in fact, what is sound? Sound is a pressure wave. A pressure wave is where particles move back and forth based on an oscillating pressure. And that most definitely does occur in the universe, most specifically in the creation of the universe itself. We have what's called a baryonic oscillations. We'll be getting into this in the next to last lecture of this course. So you could make that argument. Oh, thank you. Brahe lost his nose to his third cousin. Thank you so much. Unrelated to this lecture, what is the moon material made of? This is a fascinating subject, and I wish I had a whole lecture for this. So, we went to the moon because we wanted to beat the Russians. It really had to do with, science per se. And in fact, in recent released audio tapes, John F. Kennedy was reported as saying he didn't really care about the moon. He didn't care about space at all. But so we brought back hundreds of pounds of moon rocks. Here's the thing. The composition of those moon rocks matched the Earth composition exactly. I mean, exactly, down to the 7th decimal point. And that was something nobody expected. And the only way that could have happened is that the Earth and the moon were one and the same at some point in its past. And we now know that in 4.52 billion years ago, the proto-Earth was completely destroyed by the impact of another planet about the size of Mars. And when that protoplanet hit the Earth, both of them were turned into this molten ball of stuff. And it was spinning so rapidly that it spun off a chunk of it, which became the moon. The reason why this is so surprising is no other heavenly body comes even close to matching the Earth's composition. Every asteroid, every meteorite that impacts the Earth has a vastly different composition. So this was a huge, huge surprise. So the moon is made of Earth stuff. the eccentricity related to its distance from the sun? It's related to how the distance varies. So if the distance from the sun varies over its orbit, then it's highly elliptical. Can a star become a planet? Depends on definitions. So Jupiter. Jupiter is very large. It's a tenth the size of our sun. And it has internal heat because its gravitational force at the center of it is very strong. Jupiter was only 10 times more massive than it is now. And remember, Jupiter is 1,000th the mass of the sun. It would actually be a sun. And so the difference between a planet and a star is a kind of fuzzy thing. And some people use the term brown stars to refer to very, very small stars that are basically Jupiter-sized. Let's see. How are you able to map where the asteroids are? Yeah, good question. What you do is you point up a telescope, and when you point up a telescope, you match the motion of your telescope with the motion of the celestial sphere. The stars show up as little dots. But if you do that and there are streaks that go across the image that you just took of the celestial sphere, well, those streaks could be passing planes. Those streaks could be planets. But you can calculate if they're planes. You can eliminate those. If they're planets, you know where the planets are. And then there are streaks that you can't identify, and those streaks are asteroids. They're streaks because they're moving with a considerable speed across the celestial sphere. And so now you've got these streaks. You've identified that they're asteroids, and then you can move your telescope so it matches the motion of those streaks. And then you can calculate its orbital parameters, and you can say, well, it's the body of a certain size because it's a certain brightness, and it's got a certain orbit, and that orbit puts it between Mars and Jupiter, QED. You've just discovered an asteroid. And we discover them periodically, even today. How do they find out that the universe is expanding? Well, we've got an entire lecture on that, just that single topic, so we'll get into that. Does anyone have idea what system Ubababana came from? So people have guessed. The problem is that the closest match we have is like 50 light years away. And in fact, the closest, and the problem is that over tens to hundreds of millions of years, the stars are all moving around almost chaotically. And so we can only guess which star it came from. But whatever star it came from, it's been headed towards us for a very, very, very long time. Any other questions? If you ask me a question I didn't answer, it's because it scrolled down so quickly. So if I didn't answer your question, go ahead and type it in again. What is your favorite or most interesting cosmic phenomenon? Solar eclipses. If you have a chance, you must solar eclipse. 2024 is your next chance on U.S. soil. There's lots of other chances if you don't mind traveling. But it is by far the most spectacular and emotional astronomical event you will ever observe. One problem is if you look at a telescope at these great things, it requires knowledge to really understand why this, why it's so spectacular emotionally that you're looking at a galaxy that light started its way to your eyeball 4 million years ago. But with a total solar eclipse, you don't need no knowledge. It just strikes you in your gut. So you have to see it. So Sam Wood, I guess you saw a total solar eclipse. Anybody else saw a total solar eclipse? And tell me how that experience was for you. Dark. Cute. Yeah, it was dark. Magical. Yeah, and it's not until you've actually experienced. People can talk about it, but you all have to experience it. And again, the partial solar eclipse, where only part of the sun is covered, like we saw in Raleigh, it's like hugging your sister versus getting married. It's a concept that's completely different. You have to see the total. Okay. Yeah, it was amazing. And almost spiritual, I'd have to say. Okay, so last questions before we break off, and I'll see you all on Thursday. One last question. It's like you were dark and then surrounded and full of light. Yeah. I mean, it just struck me that it was so cosmic. It's guy, boy, that's an overused term. Anyway, it's now 11:30. Thank you so much. I will see you all on Thursday.